This is a transformer. We find them everywhere. They are essential to our modern lifestyle. They provide the connection between our homes and the electrical power stations. I'm going to show you how they work, why they make this noise, and also how to calculate them in this video, which is sponsored by Skillshare. The first 1,000 people to click the link and join will get a 1-month free trial. More about that later. Transformers look something like this. We find them illustrated with symbols like these in electrical drawings. Transformers are simply a device used to transfer electrical energy. It can change the voltage and current in the process, which is very useful. However, they only work with alternating current. They do not work with direct current. Most appliances are rated in watts or kilowatts, but transformers are rated with the units VA for volt amps or even kilovolt amps. We will learn why later on in this video. We can find small transformers used on doorbells or laptop chargers. We have larger versions to supply our homes and businesses, and we also find enormous ones which supply entire regions of towns and even cities. So where have you seen transformers used? Let me know in the comment section down below. There are lots of different ways to construct a transformer. I have some small common examples here, but they are essentially just the same thing. They have two separated coils of wire wrapped around an iron core. The generator or supply is connected to one coil, known as the primary side, and then the load, which is the thing we need to provide power to, is connected to the other coil, and this is known as the secondary side. If I take this one apart, we can see there are simply two separate coils of wire and lots of sheets of iron. That's it. The transformer is just transferring power between the coils. Electricity is dangerous, so do not try this at home unless you are qualified and competent. However, you can use Skillshare from home, and like me, you can follow Marques Brownlee's very own YouTube Creators course. I've used it to improve my shots for this video, as it's packed with useful tips. Skillshare is an online learning community with thousands of courses for us creative people, where you can learn everything from improving productivity, business analytics, graphic design, photography, and even web development. I think you're going to really enjoy this. So the first 1,000 people to click the link in the video description and join will get a 1-month free trial. Do check that out, links down below. Okay, so if we use something called a step-up transformer, then we can increase the voltage on the output. If we use a step-down transformer, then we can decrease the voltage on the output. But why would we want that? Well, the power station might be producing 12,000 volts, but your home needs between 120 and 240 volts. The power station is probably a long distance away, so there's going to be a lot of resistance in the cables, resulting in huge losses of energy on the way. So instead, we use a step-up transformer to increase the voltage to around maybe 400,000 volts. Then as we reach the town, we use a step-down transformer to reduce this back to around 11,000 volts for local distribution. And then we reduce it again down to around 240 volts for our homes. By increasing the voltage through a transformer, we reduce the current. Energy loss in a cable depends on the electrical current and the resistance of the cable. If this cable has, for example, 5 ohms of resistance, and we try to send 10 kilowatts through it at 240 volts, we would lose about 87% because the current is high but the voltage is low, and so the losses are huge. But if we were to send this at 400,000 volts, we lose a tiny fraction of just 1% because the current is low. So we can transmit power further and more efficiently at higher voltages. As a side note, the reason homes in North America can have either 120 or 240 volts is because they use a 3-wire system, where an additional wire is connected to the center of the secondary coil. Therefore, we can use just half of the coil to get 120 volts, or the full coil to get 240 volts. However, most of the world uses around 230 volts, and for this they use just a 2-wire system, which is a much simpler design and allows more power to the outlets, and this is useful, for example, to quickly boil a water kettle. By the way, I have covered residential electrical systems previously in great detail. Links down below for that. When we pass an electrical current through a wire, it generates a magnetic field around the wire. If we reverse the direction of current, the magnetic field also reverses. We can see that by placing some compasses around the wire. When we connect an AC generator to a closed loop of wire, the magnetic field inside the generator is going to basically push and pull the electrons in the wire so that they constantly alternate direction between moving forwards and backwards. So the magnetic field is therefore constantly reversing. The voltage is going to vary between its maximum and minimum values because of this. That's why we see a sine wave pattern if we connect an oscilloscope to a power outlet. This pattern repeats 50 or 60 times per second, depending on whether it's a 50 or 60 Hz supply. The AC frequency in North America is 60 Hz, but most of the world is just 50 Hz. With a transformer, the frequency we put in is the frequency we get out. We can just increase or decrease the voltage, not the frequency. When we wrap the wire into a coil, this magnetic field becomes even stronger. The wire has to be insulated with an enamel coating to ensure the current flows along the entire length. Otherwise, it will just take the shortest route and it will not work. If we place a second coil of wire in close proximity to the first coil, then the magnetic field will induce a voltage into this second coil because this magnetic field is going to push and pull the electrons in the second coil, forcing them to move. This is therefore a transformer. The same thing happens if we move a magnet past a coil of wire. The magnet will induce a voltage into the coil. The key component here is that the magnetic field is constantly changing polarity as well as intensity. This disturbs the free electrons and causes them to move, and we call this electromotive force. However, this only works with alternating current. It will not work if we connect a direct current supply to the transformer. The flow of electrons will still create a magnetic field around the primary coil, but this will be constant and a fixed polarity and intensity. So it will not disturb the electrons in the secondary side. The only time it will create an electromotive force using direct current is briefly when the switch is opened and closed, because this energizes and de-energizes the magnetic field of the coil. So it is therefore changing. Or alternatively, we could change the voltage, because that will also increase and then decrease the magnetic field of the coil. Notice that when I pass a DC current through this transformer, we get a very brief voltage spike as the magnetic field increases, and also as it decreases. But if I use an AC supply, we get a constant output voltage because the magnetic field is constantly changing. And that is why we use alternating current. Now, we can just use two separate coils of wire as a transformer. It will work, but not very well. The problem is that we're wasting a lot of the magnetic field, because it's not in range of the secondary coil. So we place a ferromagnetic iron core between the coils. This concentrates the magnetic field and guides it to the secondary coil so that the transformer is more efficient. However, this is not a perfect solution. It will result in eddy currents flowing around the core, which will heat up the transformer and therefore wastes energy. To reduce this, the core is made of lots of thin laminated sheets, which restricts the eddy current movements and reduces their effects. Although we will still lose some of the magnetic field due to leakage flux, and we also get some losses due to the disturbances caused at the joints. We also lose energy in the wire and the coils, because they will always have some resistance, and this generates heat. So in a transformer, we have copper losses as well as iron losses. The alternating current causes the sheets to expand and contract tiny amounts, which causes vibrations between the sheets, and this is why we get that humming sound. A step-up transformer works simply by having more turns of wire on the secondary side. This increases the voltage, but it decreases the current. A step-down transformer works by having less turns of wire on the secondary side. This reduces the voltage, but increases the current. Now, this isn't a magical device that produces more energy than it receives. For example, a step-down transformer might receive 240 volts, and it outputs 120 volts. We see that the voltage halves, but the current doubles. If we multiply the voltage and current, we see the same value on each side. This is the volt-amp value, which is power, or apparent power. And that has to remain the same. So if the voltage changes, then the current has to change in proportion to maintain the power. So why do transformers use the units of kVA instead of kilowatts? Well, the transformer is just transferring power between the coils. So we use the volt-amp unit. The kilowatts depend on what you connect to the transformer. The manufacturer doesn't know what you will connect to the transformer. So they state the total rated apparent power in volt-amps. And that's because in AC circuits, the load depends on the true power in kilowatts and the power factor, which is basically efficiency. And this varies depending on the device. Some energy is consumed, but it produces no work. It is just wasted as heat, and we call this reactive power with the units VAR. Power factor is just the ratio of true power and apparent power. If you think of a glass of beer, the liquid beer is the useful stuff. This is your true power in kilowatts. But there is always some foam which is useless. We don't want that. This is the reactive power, or the volt-amp reactive. You pay for the total volume of the glass, regardless of how much foam and beer is inside. This is your apparent power in volt-amps. Now, if you have a good bartender, you will get a little foam and lots of beer for your money. But if you have a bad bartender, then you're going to get lots of foam and not so much beer for your money. The transformer manufacturer is basically saying this transformer can handle a glass this big, but it's up to you how much beer and foam you put into that. The less foam you try to pass through, the more beer you can get out. So, the more efficient the device is that you connect, the more things you can power. Transformers are also often used in rectifier circuits to convert alternating current into direct current. The transformer first reduces the voltage, and then some diodes convert this into a rough direct current. A capacitor then smooths this out into a nice clean power supply. You can learn how that works in detail in our previous video. Links down below for that. Let's run some basic calculations for transformers, assuming it is perfect with no losses. If we had a transformer with 1000 turns on the primary and 100 turns on the secondary, and we supplied it with 120 volts, what voltage would we see on the secondary side? We can use this formula to find that out, and we see the answer is 12 volts. So this is a step-down transformer. What if we only knew the output voltage and the amount of turns? Well, we could find the input voltage using this formula, and if we input the values, we get this answer. If we wanted to find the number of turns on the secondary side, and we knew the voltages and primary turns, then we could use this formula to get our answer. If we wanted to find the number of turns on the primary side, we could use this formula, and this will give us the answer. If we had a current of 1.2 amps on the secondary, then we find the primary current using this formula, and we see the answer is 0.12 amps. We could also find the answer if we knew the secondary current and both voltages by using this formula. If we knew the current on the primary side and the voltages of the primary and secondary, we could find the secondary current using this formula. Or we could also find the answer by using this formula. We then check that the power is the same on both sides of the transformer by multiplying the voltage and current. Let's now consider some step-up transformer examples. If we had 100 turns on the primary and 200 on the secondary, and we supplied it with 120 volts, what voltage would we see on the secondary? Well, we can use this formula to find that out. So we see the answer is 240 volts. So this is therefore a step-up transformer. What if we only knew the output voltage and the amount of turns? Well, we could find the input voltage with this formula. If we wanted to find the number of turns on the secondary side, and we knew the voltage and primary turns, then we could use this formula. If we wanted to find the number of turns on the primary, then we could use this formula. If we had a current of 1 amps on the secondary, then we find the primary current by using this formula, and we see the answer is 2 amps. We could also find the answer if we knew the secondary current and both voltages, by using this formula. If we knew the current on the primary side and the voltage of the primary and secondary, we could find the secondary current by using this formula. Or we could also find the answer by using this formula, if we knew the number of turns. And then we check the power is the same on both sides of the transformer by multiplying the voltage and current. Check out one of these videos to continue learning about electrical engineering, and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, LinkedIn, Instagram, TikTok, as well as theengineeringmindset.com.